Welcome to my data center technical series. This is a review for volumes 1 through 3. As I was going back through all these videos, I noticed how much information I did not include in regards to all these different subjects of topics that I'm talking about with analog to digital converters, input divider circuits, also molded case breakers, thermal runaway, tripping mechanisms, normally open, normally closed, shunt trip, UVR, and so on and so forth. So let's just go through very briefly on reviewing an analog to digital converter, but also I wanted to review the mathematical relationship that will help us understand and determine the theoretical resolution of an ADC. So let's go through this really quick. An ADC is going to transform an input analog to digital analog voltage to a binary number, a series of ones and zeros, and then to a digital number, a base 10, for any kind of battery monitor or UPS, power system inverter, anything that's being fed into a BMS or a supervisory control and data acquisition system. Now this number of binary digits or bits is going to represent the digital number that determines the ADC resolution. However, that number is only an approximation of the true value of the analog voltage at any particular instant, because the voltage can be represented both digitally in discrete steps. So what we need to do is look at the approximation of this analog value and then put a simple formula in there that's going to help us understand it. So this formula relationship is essentially an input divided by 2n. Now 2n would be 2 to the 12th power for 4096 counts, or 4.096 volts, or 2 to the 16th power for 65,536 counts for a 16-bit analog to digital converter. And when you see that 10-volt scale, we're scaling everything down, divided by 4096, gives us a resolution on the 12-bit analog to digital converter of 0.00244 VDC, or 2.44 millivolts. Now if we do the same thing, same scale for 16-bit, it's going to show you that you have a 0.153 millivolt scale. You can already see exponentially in orders of magnitude the resolution increase, but this is usually specified with respect to the full range reading of the ADC and not respect to the measured value at any particular instant. What we're not doing here in the resolution is taking into account all of the other components of the circuit. So you have operational amplifiers, you have gain, you have offset, you have loss of code, you have quantization. There's a lot of other issues that we have to take into account here within ADCs, and that's why I always have an issue when someone says, oh, I use a 16-bit ADC, but the resolution of their ADC is more like 13. So let's step through some of that stuff now, and we'll get started. Let's go. Analog to digital converter, accuracy versus resolution. Now every single ADC measurement will contain a plethora of unavoidable independent errors that influence its accuracy. Now where you see OI, this is going to represent every single independent error in the circuit. Now the total error deviation rate can be shown as this equation, which is including the variety of errors such as sensor anomalies, amplifier gain, ADC, quantization, resolution error, offset, and noise. And that's what you're going to see. There's the total divided by the square root of EI over OI squared. So this error the resolution rate is very, very important, because again, if you look at it specifically, where we're going to look at a little bit later, where we're looking at the number of bits that can be utilized in the system, this is the formula that you're going to utilize to understand the accuracy versus resolution. But let's look at the quantization error. Now in a theoretical world, a perfect ADC with an input analog voltage measurement should be represented by a unique digital code accurate to an infinite number of digits. But in the real world, ADCs have small, finite gaps that exist between a digital number and a consecutive digital number. And this amount depends on the smallest quantum value that the ADC can resolve. Now in the case of the 12-bit analog to digital converter covering a 10-volt range, that quantum value is, as we showed previously, 2.44 millivolts, the least significant bit. But that input voltage range is partitioned into a discrete number of values the converter can measure, which is also the ADC resolution. So we have to look at the quantization error. In this case, is specified to mean no more than 50% of that LSB, the least significant bit. So for the 12-bit ADC, analog to digital converter, the error rate is plus or minus 1.22 millivolts, or 0.0122%. Now these ADC errors are typically specified in 3 different ways. The error in the least significant bit, the voltage error for a specified range, and the percentage of the reading error. Now, as I'll tell you this is an honest to God statement. Most ADCs are not as accurate as the manufacturer state or as is according to their specified resolution, mostly because other errors will contribute to the overall errors such as gain, linearity, offset, missing codes, again because of quantization and noise, and all of these things need to be taken into account when you're looking at the quality of a product, okay? So the next thing we're gonna look at when we move on here is just a little bit more into calibration of these input circuits and some more information that I think is very applicable for you all out there, for you electrical engineers and you people working in the data center industry. Let's get going. Effective number of bits. Now the effective number of bits should demonstrate that the actual system measurement accuracy is much less than the ADC bit accuracy specifications. For example, most manufacturers will state, hey, our device uses a 16-bit analog to digital converter, but the results of that type of standard test, which is the ENOB test here, will show that the performance is actually much closer to a 12 or 13-bit system because of all the linearity, offset, noise, gain issues of the entire system. Now, as we look at this evaluation of the data acquisition system as it performs in the real world versus what the manufacturers say in their lab, we have to test all of the cables and connections and operational amplifiers, and we have to consider the front end of the data acquisition system, the ADC, the multiplexer, again, the programmable operational gain amplifier, the sample and hold amplifiers. All of these individual circuits will affect the digitized output from the DAC and any and all nonlinearities such as noise, distortion, quantization, and other types of anomalies will sneak into that front end of the unit, and it may only be in one channel or multi-channel. It could be across all. It could be crosstalk. It could be even some errors will creep up from the effect of one channel through crosstalk on the PCB. So testing systems with an ENOB will provide a valid benchmark of the system capabilities and its accuracy. It's not the specification or a replacement for like a noise ratio and other error specifications provided by the manufacturer, but the ENOB test, when compared with all of the other types of input variables, can give you a very stable understanding of what the system is capable of in a noisy environment, specifically in power systems. So let's keep going here. We're going to go into the breakers. I'm going to touch just very briefly on thermal runaway, some other mechanism systems, including on lithium-ion systems, LIB, and then we'll go into more specifically a few other variables and input things I'm discussing in tripping the breaker and how the UPS provides that signal. Let's jump in now. Thermal runaway, understanding the fundamentals to this catastrophically dangerous situation and relating to electrochemical generating devices is very important. So let's look at this really quick, and then I'll jump back into a few other components of review that I want to kind of dial in. But let's look at thermal runaway. Now, this is going to occur when a cell or an area within the cell is going to have an elevated temperature due to a thermal failure, a mechanical failure, an external or an internal short circuiting or a ground fault or electrochemical abuse, hitting it cyclically thousands of times, or very deep depth of discharges. When the temperature elevates, an exothermic decomposition of the cell material begins, and eventually the self-heating rate of the cell is greater than the rate at which the heat can be dissipated to the surrounding area, and the cell temperature rises exponentially, and the stability is ultimately lost. Now, the loss in stability results in the remaining thermal and electrical chemical energy being released into their surroundings. You can actually see that here. I've seen batteries fail like this all over the world. Valve-regulated lead-acid batteries, vented lead-acid batteries, NiCad batteries, and now lithium batteries, LIB, which is coming into the data center area. Now, something that Tesla is also looking at, I believe they're looking at implementing certain materials like triphenyl phosphate and having a separator 5 millimeters. And they're also looking at vacuum tubes and so on and so forth to open those tubes if one of the systems starts to draw too much current. And we previously talked about, and V2 in the volume 2, tripping the breaker mechanism using a shunt. And I had a great question that somebody had asked was, where do you install the shunt? Well, the shunt would be installed over one of the inner tiers. So if you had 40 to 12 volt mono blocks, 540 volt DC bus, each of the inter tiers would be on inter tier 4 or 8 or 12 or 16. You could put a large shunt in series, going from the negative of 4 to the positive of 5, and then you would calibrate that appropriately, have it come into some kind of a microprocessor or a microcontroller. You can even use Raspberry Pi stuff, which is something I'm testing now, and what you want to do is essentially trip that if it goes over 1 amp or 750 milliamps or 1.5 amps, whatever that signal threshold that you programmed into the monitoring system is, you want it to trigger. Now remember that UVR and shunt trip, that voltage is coming from the UPS. So it's either 48 volts or 24 volts, and it's either being constantly supplied or it's not being constantly supplied and the breaker just closes, and if they need to trip it, they send a signal out to the normally open or normally closed contacts and it'll trip the breaker, okay? So all of this stuff can be integrated, and it's very important that it should be. It is necessary, because once this thermal runaway mechanism occurs, trying to implement some kind of a thermal management after the fact, being reactive instead of proactive is not going to behoove you or your organization or your manufacturer, the people that you procure your equipment from. They need to design these protection systems in order to safely utilize all types of energy storage systems across all of the markets. It's vital that we implement this stuff and also educate everyone on the importance of thermal runaway systems, because as we've seen in the years past, it can even happen on your cell phones, right? I mean, I think about that quite often when I get on airplanes and we have 300 cell phones, all with, batteries that have really high energy density packed in. And that's for me, as someone who's worked in the battery industry for almost 20 years, I look at the lithium ion implementation coming into the fray. Now, valve regulated lead acid batteries are 99% recyclable, and they're, as compared to the energy density on a footprint wise, now we're going to start installing lithium batteries in data centers that are 1/5 the size, 1/5 the weight, but 3 times the energy density, and having a thermal runaway mitigating design or system, and as I say, hybrid systems, not just one, where you would have a material science component of this, triphenyl phosphate, or some kind of other material that is going to mitigate that expansion, that exothermic heat generation. You need to have that in place. There's some separators, vacuum tubes. You don't want to have just one mono block. You need to separate everything with glass matting. There's so many different implementations when it comes down to just looking at the pure science of generating energy and then storing it, but also understanding the decomposition and reactions of entropy and exothermic generation, of temperature variation. These things are not really at the top of everyone's importance list when they're building data centers out, when they're trying to meet a specification, when they have these construction builds. 18 months, we got to have 1 megawatt out the door, 5 megawatts, and 150 acres, whatever you have for your data center, your edge facility, and so on and so forth. But looking at this stuff, as I've stated previously, only one battery. It only takes one battery to melt down a data center, to melt down a wing. And this can cause explosions. It can cause water leaks. I've seen one battery cause $50 million worth of damage at one facility, not only because of the fire, because of the mitigation systems that were on site, right? So all of a sudden, all the water systems spray on. Now you got servers that are flooded with 3 feet of water. It is catastrophic. And if you don't design these variables into your data center infrastructure, then you're going to suffer a catastrophic outage eventually. And being proactive, not reactive, is the way forward. Okay, so let's move on just a little bit forward into some of the impedance versus conductance versus DC resistance methodologies. I kind of very skimmed over the top of a lot of that information, and I think there's quite a bit more there that can be helpful to you. So let's get started. Let's very briefly review DC resistance, which is purely resistive and has no capacitive reactance, versus AC impedance conductance-based methodologies. Now, I'm a proponent of DC resistance mainly because it's been used for a long time. It's one of the oldest and most reliable test methodologies, and it generally only lasts a few seconds, and the load current can be anywhere between 20 and 100 amps depending on the battery size. And as we reviewed in the first iteration of the volume series, all we're doing is looking at the voltage drop divided by the current, and that's going to provide a resistance value based on Ohm's law. Now, these values are very accurate, they're repeatable, they're not impacted by noise. and the resolution is generally in the micro ohm or in the millions of ohms versus many of the other ones. Now, if you look at the Randall's model equivalent circuit for batteries, you see resistive elements, R1 and R2, and these systems, for the DC system, it's going to ignore completely the capacitive reactance of the battery. Now, the capacitive reactance, or in C, about 1.5 farads per 100 amp hours, is a very important component of the battery, and this is where AC conductance and impedance methodologies are drastically impacted. So if you look all the way up here, look at all that noise riding on any kind of a signal. I see this even on DC buses constantly, and we'll get into this when we review instantaneous gate bipolar transistors, IGBTs, and silicon-controlled rectifiers, essentially, charging mechanisms on inverters and big power systems. AC-based methodologies, depending on the injection source. So what they're doing instead of DC is they're injecting an AC signal into the battery across the anode and cathode. That frequency can vary from 50 hertz to 1,000 hertz, whatever they're going to choose depending on the capacitive reactance. I've always hoped that they have an intelligent system there that can see that there's noise riding in the DC floor, and they can switch the frequency to 500 hertz to mitigate this. I haven't seen a system that does this yet, but we'll see in the future. But at specific frequencies, the inductive and capacitive reactance can converge and it will result in a minimal voltage lag. Now, generally what they have here, if you look at that same Randall circuit, because of the capacitive reactance, a single frequency testing methodology will see all of the components as one complex impedance. They call that the modulus of Z. Now, the majority of that contribution is coming from the conductance of the first resistor, right? So what this means is, in very basic terms, is that AC-based testing methodologies, if you take all of the noise out of the equation completely, like that's gone, there's no noise, it's a perfect power system, zero noise, switching at 60 kHz like a Toshiba G9000, it's the most efficient UPS on the planet, and with the lowest possible measurement of noise on the DC bus. Even if you take all of that, AC-based technologies are not going to see a bad battery until it's completely open. And you ask why? Because most of it is only looking at one component of the battery, and everything else is grouped into one package, where the DC resistance is able to actually identify individual components of the battery in relation even to torque and electrochemical degradation, dry out in the glass matting. This is why I do not see single frequency testing methodologies or products as advantageous, and I'm a huge proponent of using multiple frequency electrochemical impedance spectroscopy. What this is doing, and I think there's only one company called Cadex that actually uses this in the market. I'm surprised I don't see it more in the data center industry, especially with lithium coming in, coming into all the different facilities now. These types of instruments inject, from 8 to 30 different excitation frequencies at various frequencies. And here's the important component of this. Every material of the battery reacts to a frequency differently. This is outside of capacitive reactance, right? But those sinusoidal signals are regulated at various millivolt steps to remain within the battery voltage of the battery. And this is kind of difficult generally if you're using a single frequency, but if you're using a lot of different frequencies, what this can do is, with a multi-frequency spectroscopy device, you can actually calculate multiple resistance values based on that Randall's model that you see here. And it's really, really amazing. And it does it very, very quickly. It can do 10, 20, 30, 40, 50 million measurements very, very quickly, and it's not loading the battery like a DC a DC load bank using a purely resistive element there. So I think it's important to understand the differences between the technologies. On DC plants, I don't have an issue using AC-based meters because there isn't that much noise. But on big power systems, older power systems, maybe low quality power systems, and big UPS is 1 megawatt, maybe where they don't have a transformerless design, where noise is backfeeding from the switch mode power supply downstream in the load through the inverter. Again, everything goes into the battery system as a sink. There's a lot of noise there. I see signals, as I stated previously, up to 5 to 10 to 15 amps at various frequencies, cycling the batteries constantly, and you can literally feel it when you enter the room, the battery room that has those components riding in the bus and the DC bus. is anywhere between 5 and 12 degrees hotter. And as I've stated previously, batteries are designed to operate, most batteries are designed to operate at 25 degrees Celsius or 77 degrees Fahrenheit. You take the Celsius times 1.8 plus 32, you get your Fahrenheit. There is some new technologies like Tesla's working on metal air and even the Enersys thin plate pure lead batteries, which are designed to operate at higher temperatures so you can increase the temperature in your data center, thus saving some money on cooling. I mean, that's a big difference, 18, 20 degrees there. So it's important to understand all of these different variables when we're looking at the delta V on the battery system as well. Let me come back to that. In the first video, I only reviewed V2 minus V1, but also remember that entire voltage reflection, the reflection coefficient, we can take values all the way up this delta, all the way up that delta as it's releasing on that coup de foie, or the tail of the whip, right? So we can take, not just V2 minus V1, but V2.1.2.3.4.5.6.7.8.9.10, and we can average that all the way up and get a much cleaner signal that can provide us an estimation of the battery conductivity, capacity, and state of health moving forward. Thank you so much for tuning in to this review of volumes 1, 2, and 3. And I'll move on to volumes 4, 5, 6, and beyond. And I thank you guys for tuning in. Thank you for really giving me a lot of energy and feedback. It means the world to me. God bless. Have a wonderful day.